On July 24, 2001, a radio pulse lasting only a few milliseconds hit the Parkes telescope data, but it was not recognized as the first fast radio burst until 2007. That delay is the perfect opening clue. The signal was real. The source was not obvious. And the energy implied by the distance looked absurd. Today we call it the Lorimer burst, or FRB 010724. Confirmed, fast radio bursts are millisecond radio flashes from space. Confirmed, many are extragalactic. Disputed, whether one engine explains all of them. So the mystery is not just what made the first burst. It is why the universe keeps making flashes that vanish before we can turn our telescopes fast enough. Here is the first evidence payoff. A fast radio burst is a brief spike of radio energy, usually lasting milliseconds. The signal arrives with a measurable delay across radio frequencies. That delay is called dispersion measure. It tells astronomers the burst passed through plasma between the source and Earth. Higher dispersion usually means more material, and often greater distance. That is why FRBs became so valuable. They are not just mysterious fireworks. They can act like probes through the invisible matter between galaxies. The mystery signal became a cosmic measuring tool. The timeline changed quickly. First came one strange archival burst. Then more events appeared in old data. Then telescopes began catching them live. Then CHIME changed the scale of the problem. The first CHIME catalog reported 536 bursts from its early survey period. The second CHIME catalog, released in 2026, reported 4,539 bursts from 3,641 unique sources, including hundreds of bursts from known repeaters. That is the turning point. FRBs are no longer one weird anomaly. They are a population. And once you have a population, the mystery becomes statistical. Fast radio bursts do not point to one haunted region of the sky. They appear across many directions, with telescope sensitivity shaping what we detect. That matters because a scattered sky distribution argues against a local Earth-based trick. It also means the source class is probably common enough to occur across cosmic history. Confirmed, FRBs come from many sky positions. Confirmed, selection effects matter because telescopes do not see the whole sky the same way. Interpretive, the real pattern is not a treasure map to one object. It is a census of extreme engines. The repeater clue changed the debate. If an FRB repeats from the same location, the source probably survives the burst. That makes one-time catastrophic explanations harder for that class. The famous repeater FRB 121102 helped prove that at least some sources can fire again and again. CHIME later found many more repeaters. In recent catalog work, only a small fraction of sources have been observed to repeat, but the data does not prove that non-repeaters are a separate species. Some may simply repeat too rarely for us to catch. Confirmed, repeaters exist. Disputed, whether repeaters and apparent one-offs are fundamentally different populations. Then came the closest major clue. On April 28, 2020, a burst called FRB 200428 was detected from the direction of SGR 1935 plus 2154, a magnetar inside our own Milky Way. That mattered because magnetars are neutron stars with extreme magnetic fields. For the first time, an FRB-like radio burst was linked to a known galactic source, with high-energy activity nearby in time. Confirmed, magnetars can produce FRB-like bursts. Disputed, whether magnetars explain every cosmological FRB. That is the careful line. FRB 200428 did not solve the whole field. It proved one engine can make the kind of flash astronomers were hunting. Magnetars make sense because FRBs demand compact violence. A millisecond burst means the source region must be small or extraordinarily synchronized. A neutron star is small enough. A magnetar has a magnetic field powerful enough to store and release extreme energy. That gives theorists a plausible engine. Starquakes. Magnetospheric reconnection. Shock waves. Plasma processes. These are not final answers. They are model families. The confirmed clue is the magnetar association. The interpretive layer is how the radio flash is actually produced. The case stays open because FRBs are diverse. Some repeat. Some have not repeated. Some are highly polarized. Some show complex frequency structure. Some sit in active star-forming environments. Some have been associated with older or quieter galaxies. Some have persistent radio sources nearby. That variety is the warning label. One mechanism may dominate. Several mechanisms may contribute. Or one engine may produce many observational phases depending on environment, beaming, and propagation. Dispersion measure is one of the most useful evidence cards. When a burst travels through ionized gas, lower radio frequencies arrive later than higher ones. That sweep lets astronomers estimate how much free electron material the signal crossed. For distant FRBs, that can help map otherwise invisible matter between galaxies. So the same feature that made the first bursts look strange became a scientific advantage. Confirmed, dispersion is measurable. Interpretive, FRBs may become tools for weighing the cosmic web. That is why this mystery is valuable even before every source is identified. Compare the two boards. Solved piece, fast radio bursts are real astrophysical radio flashes, many from outside the Milky Way. Solved piece, magnetars can produce FRB-like bursts. Open case, whether all FRBs are magnetars. Open case, why some repeat and others have not. Open case, how burst energy becomes coherent radio emission. Open case, why environments differ so much. This is the honest version. The mystery has moved. It is no longer, are FRBs real? It is, which engines produce which bursts, and what can those bursts reveal about the universe? What would strengthen the case? More precise localizations to host galaxies. Simultaneous radio, X-ray, gamma ray, and optical monitoring. Repeat detections from the same source. Polarization and spectrum measurements. A clear link between a burst and a physical event on a magnetar. And public catalogs that let researchers compare populations without cherry-picking. That last part matters. FRBs are too fast for mythology alone. They need statistics, timestamps, frequencies, and sky coordinates. FRBs pull views because the hook is almost unfairly strong. A signal from deep space. A flash lasting milliseconds. Energy beyond ordinary imagination. Repeaters that act like cosmic lighthouses without a visible lamp. And a magnetar clue that feels like science fiction, but is real astrophysics. The danger is exaggeration. The opportunity is clarity. The best video does not say aliens. It says, here is the signal, here is the clock, here is the dispersion, here is the source candidate, and here is what we still cannot prove. The real fast radio burst mystery is not a single question anymore. It is a family of questions. What makes the flash? Why does it last milliseconds? Why do some sources repeat? Why do some live in surprising galaxies? And how can a signal so brief map matter spread across billions of light-years? That is why FRBs are special. They began as an anomaly in archived data. Now they are one of astronomy's sharpest probes. The universe blinked. And the blink became a measuring stick. If fast radio bursts made you rethink cosmic mysteries, stay with the Mystery Atlas TV. We follow signals where the evidence is real, the explanation is partial, and the next detection can change the map. For FRBs, what clue would convince you most? A repeating magnetar burst? A simultaneous X-ray flash? A host galaxy pattern? Or a catalog showing one engine explains them all? Tell me your proof standard before the next signal arrives.